Okay. All right. So, all right. Let's look at this first one here. Yesterday we were looking at finite sequences, and that word finite means it ends. Okay. Finite being the opposite of infinite. Infinite's a word you've probably heard a lot more than finite. Infinite means, of course, that it goes on forever and ever and ever and ever. Yesterday we were looking at sequences that ended. So whenever we did a sum, we were only looking at maybe the first 7 terms. We didn't keep on adding them up forever. But today we're going to look at infinite sequences and series. And we're also going to look at some sequences that are not arithmetic or geometric series. For example, I have the sequence 1, 1/2, 1/3, 1/4, 1/5. Okay, so in this sequence, I am changing it. It looks almost arithmetic. Arithmetic means you're adding something each time. You're definitely adding 1, but only to the denominator. So in arithmetic sequence, you would have to be adding a number to the whole sum. So like you could, or subtracting, like if you went from 1 to 1/2, you'd have to subtract 1/2. Well, then if you subtract 1/2 again, you should have 0, not 1/3. So in this case, this is neither an arithmetic nor a geometric sequence. And so what I want us to do is to write a formula for it. And just like an equation, not a recursive formula, because we can't really write a recursive formula so easily for this. So if we just write a formula for this particular sequence, then we can write it a couple ways. We could just write it like y equals 1 over x. So like if you plug in 1, you get 1 over 1, which is 1. If you plug in 2, you get 1 over 2, which is 2. Plug in 3, you get 1 over 3. You get 1/2, and then 1/3, and then 1/4, and 1/5, and 1/6. So this would give you this sequence. However, sometimes this is also written with with recursive notation, even though it's not really a recursive formula. So they might write it like this: a sub n equals 1 over n. This is using that same notation for a recursive formula, because a sub n tells you, like if you have a sub 1, that means your first term. If you have a sub 2, that means your second term. If you have a sub 5, that's your 5th term. But it's not actually a recursive formula, because a recursive formula depends on the term in front of it. So this does not depend on the term in front of it. It's just whatever term you have, it's 1 over that number. So if it's actually a recursive formula, you'll see like a sub n minus 1 or a sub n plus 1 somewhere. But that really is not important for what we're doing. What I want to know is, as n approaches infinity, a sub n approaches what? Okay, so as n gets bigger and bigger and bigger and bigger, okay, what is the value of a sub n going to get closer and closer and closer to, is what this question is asking. So like let's just do, so like we know a sub 1 is 1 over 1, which is 1. All right, a sub 2 is 1 over 2, 1/2. A sub 3 is 1 over 3. Okay, so right now, what is happening to the value? Is it increasing or decreasing? It's decreasing. All right, let's skip several numbers right here. Okay, a sub 10. Okay, that is 1/10. 1/10 is smaller than 1, right? 1/10 is smaller than 1/3. What we're doing here is we're taking a pizza and we're cutting that pizza into more and more and more and more pieces. And when you do that, each tiny little piece gets smaller and smaller and smaller, right? So 1/10 is smaller than 1/3. What about if I cut my pizza into 100 pieces? Each little piece is 1/100th of the pizza now. So first of all, almost impossible to actually physically do with a pizza. But let's say I was able to do it. Are you going to get much pizza whenever I pass it out? No. What about 1 over 1 million? That gives you 1 over 1 million. 1/1,000,000th. If I can cut that pizza into 1,000,000 pieces, which is unlikely that I would be able to do that, but let's say that somehow I could. Are you going to still be hungry after you eat your piece of pizza if I only give you one? Yes, you will be starving because it will just be a crumb, right? So, so these numbers are getting smaller and smaller and smaller and smaller and smaller. Here's my question. What number is that value getting closer to? 0, right? Every time I cut that pizza more, then your amount of pizza you're getting is getting closer and closer and closer and closer and closer to nothing, right? So, as n approaches infinity, a sub n approaches 0. It'll never become negative, right? Because I still have a pizza, so there's like tiny little microscopic pieces of pizza that remain. It won't be negative, but it gets closer and closer and closer and closer to nothing, right? So that is going to be like the key principle that we're going to be looking at in this section. So let's look at these. Oh, I need to write something else here. Okay, so where we did this, I want to use what we call limit notation for this. So let me write this with limit notation. The limit, we will put LIM. And then underneath LIM, we're going to put N, and we're going to put an arrow, and we're going to put an infinity sign. So as N approaches infinity, and this is of a sub n. So when I see this notation, I know that it means what is the limit as n approaches infinity of a sub n, or as n approaches infinity, what happens to the value of a sub n? Okay, and so this, of course, equals 0 here. And today we're only going to be looking at n approaching infinity or possibly negative infinity. We can also look at n approaching different numbers, which we'll see when we get into chapter 15, which I'm putting 12 and 15 together. So whenever I look at these limits on the next slide, the first one says limit as x approaches infinity of 1 over x squared. Okay, so what you're doing here is you're starting off with x, and you want the numbers for x to get larger and larger and larger and larger and larger. So for example, if we do the same thing we did before, if I plug in 1, I get 1 over 1, right? If I plug in, let's see, hold on. If I plug in 2, I would get 1 over 2 squared, which is 4, right? If I plug in 3, I get 1 over 3 squared, which is 9. If I plug in 4, I get 1 over 16, right? If I skip on up and plug in 100, 1. No, hold on, sorry. If I plug in 10, I'll get 100. So I've got 1 over 100. What value are those fractions approaching? What do they get closer and closer and closer to? They get closer and closer and closer to 0, just like 1 over x, right? They're going to get to 0 faster. Well, actually, technically, they never get to 0 because there's always 1 over some huge number that still theoretically exists, right? If we're cutting the pizza, once you get on up past, you know, I don't know, once you get past 100, if you could ever even make it to 100, it doesn't even matter anymore. Nobody wants the pizza because it's such a tiny piece, it's not even going to help you out any. But theoretically, with that pizza, you're going to be cutting it into pieces, like more pieces each time. So it would get closer to 0 quicker for 1 over x squared. But at infinity, it doesn't matter, it's still 0, right? What about number 2 if I have 20,000 over x? Okay, so I would start off and I'd do like 20,000 divided by 1, which would be 20,000. And then I'd have 20,000 divided by 2, which would be 10,000. And then I'd have 20,000 divided by 3, and 20,000 divided by 4, and so on and so on. Eventually, at one point, I'm going to have 20,000 divided by 20,000, right? 20,000 divided by 20,000 would give me 1. After that, I might have 20,000 over 10, or 20,000 over 100,000, or 20,000 over a million, or 20,000 over a gazillion. What's going to happen to that value? What does it get closer and closer and closer to? It gets closer and closer and closer and closer to 0 too. So for example, let's say we had 20,000 pizzas, right? And if we cut them in, if we didn't cut them, we cut them, or let's say I guess cut them, I guess 1 would be not cutting them at all. We didn't cut them at all, we got 20,000 pizzas, and if I pass out the piece, one person gets 20,000 pizzas. But let's split them among the whole school, then we got to divide it by 400. So we got to cut our 20,000 pizzas into 400 times, right? So that would still be a whole lot of pizza. But if we decided to share it with the whole town of Elkin, our 20,000 pizzas, now not everybody's getting quite as much. If we share our 20,000 pizzas with all of North Carolina, now you're getting into, I'm not sure the population, but it's in the millions. So now you're getting into, oh, nobody's got much pizza left. So even though we started with 20,000 pizzas, as you go to infinity, right, it becomes nothing, right? Even if we had a gazillion pizzas, if we went to infinity, eventually it would be nothing. So a property of limits that you need to know here. The limit as x approaches infinity of 1 over n to the r power always equals 0. And actually, we could, and here r does have to be greater than 0, because what happens if I have 1 over x to the negative 3? What do I do with negative exponents? If I was solving, I would cube root, but like just to simplify it, I move it to the other side of the fraction, right? So 1 over x to the negative 3 is really just x to the third. So that would not be 0. But as long as we have a positive exponent, 1 over an x or an n or whatever variable you're using to any power is going to be 0. Also, we could, if we wanted, I guess, say this: the limit as x approaches infinity of, really, if that's x, that should be an x right there. That's my typo. But limit as x approaches infinity of k over x to the r is going to equal 0 here, where k is a constant. So that says constant there, even though you can't read it. So no matter what number you have, whether it's 1 or whether it's 5 or whether it's 20,000 or whether it's negative a million, if you are dividing it by x to any power, as the x gets bigger and bigger and bigger and bigger, it's going to be 0. Okay. A few more properties of limits that we need to know. If I have limits where I have limit of f of x plus g of x, two separate functions, I can separate those out into separate limits. I could do the limit as x approaches infinity of f and the limit as x approaches infinity of g. The same thing is true for multiplication. If I have a limit of two things that are multiplied, then I can do the limit of f times the limit of g, do the limit separately. Same thing is true for division. If I have the limit of f over g, then I can do the limit of f over the limit of g. Okay. This last one, the limit as x approaches infinity of c equals c. this is like if I had this, if I have, actually my first example, let's see, is my first example that? No, okay. So this is like this, if I had the limit as x approaches infinity of 7. Does 7 have an x with it? It does not. So is the x going to affect that 7 at all? 7 is just 7. So if it doesn't have an x with it, it just is that number, right? Okay, so these are all some properties of limits that we're going to use. Let's look at this next problem. I give you this next problem in this manner because your textbook is going to do this. I do not like this notation. In calculus, our book does not do this, but your textbook does this, so I'm going to show you what this looks like. We are supposed to find the limit as x approaches infinity of a sub n if, and actually I guess that n right there should be, that should be an n instead of an x. I've not typed that correctly. So find the limit as n approaches infinity of a sub n if a sub n equals 9/5, 16/4, 65 over 27, ... 7n squared plus 2 over 2n squared plus 3n. Okay, they gave you this. They could have given it to you without that very last term, and then you would have had to figure out the formula for it. I am not going to do that to you unless it is a very simple formula. Like the very first one that we did was 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. So that formula was 1 over x, so or 1 over n. So that I might give to you. But something like this, I will make sure that if I give it to you on a quiz or a test, that it's got this part if I word it like this. So what they're really asking you to do here when they do this is they're asking you to find the limit as n approaches infinity of 7n squared plus 2 over 2n squared plus 3n. And so I cannot pull, let's see, I guess I could maybe use Desmos. Let's see, I can't pull up I can't pull up the calculator because this doesn't have it on it, but I think maybe Desmos will work. So let's see if this will work. Alright, we want 7 and, oh gosh, this is aggravating. This does not work well. Well, I don't know if I know how to type it using this. I might flip this around so I can use my keyboard. I think it'll work. Yeah, okay. So 7n to the second plus 2. Alright, I gotta do this. And then the other part is 2n to the second plus 3n. Okay, is that right? Okay. And I guess I probably should use x. Oh, no, this works. Okay. So we are looking at the value of this as x approaches infinity, right? Will it let me... Here, let's see. Let me put a slider. Sorry. It'd be easier if I could just use my calculator. No. Never mind, that's not working. Okay. Well, let's just look at the graph. Unless I can put a table. Hold on, let me fix this. Okay, we'll just look at the graph. Sorry, guys. Okay, so let's just look at this graph. Okay, so we can see the graph does all kinds of crazy stuff over here, but we're looking as x approaches infinity. So on this graph, we're looking as our x values get bigger and bigger and bigger. So if I were to, let's do this. We can do this on Desmos. This will work. Settings. All right, so on the y-axis, I'm just going to do this. Like, let's make that number bigger. So if I make it 100 or 1,000. Oh, wait, I'm doing the y. Sorry, that's not what I want. Let's go back to, let's make it 10. Okay. Why is it doing this crazy stuff? Okay, I just want that. Okay, let's make my x. There it is at 10. If I make it 100 or 1,000 or 10,000, does it look like that's ever going to make it up here to 5? Not really. If I zoom in, I'm going to be able to see it's still increasing some, but it looks like it's leveling out, like it's hitting a line that it's never going to get to, like it's got an asymptote there. Okay, and it does. And if we could look at, if you put this into y equals on your calculator and looked at your table, you would be seeing that these numbers would be getting closer and closer and closer and closer to a given value. Although sometimes it's a little bit hard to see what it's getting close to with those decimals. So let's go back to this over here, and I'm going to show you how we can figure it out without just guessing. So, this may seem a little strange, but what we're going to do to evaluate this limit in this case is we want to divide by the highest exponent from the denominator. Okay, so always the highest exponent, but the highest exponent from the denominator, not the numerator. Sometimes the numerator is higher. So if we're going to do that here, we're going to do the limit as n approaches infinity. This is important here. That limit notation, until you have your answer, until you plug in a number to get your answer, you do not, you must write that limit notation. Do not drop that limit notation until you have your answer. So every time we're doing something here, we have to keep that limit as n approaches infinity. Sometimes I'm guilty of it. Most students get lazy and they drop that. When you get to AP Calculus, you have to continue that limit notation or you don't get credit. A lot of college professors might be picky about that stuff too if you end up taking it in college. So we've got to keep that notation all the way through. So what we're going to do is we're going to divide everything in the top and the bottom of the fraction by n squared, because that's our highest exponent in the denominator. So we'll have 7n squared divided by n squared plus 2 divided by n squared over 2n squared divided by n squared plus 3n divided by n squared. Oh, let me put it up that much. So we're taking what we had and we're dividing every single term by that n squared, top and bottom. And so now we've got some stuff that will simplify. So this n squared and n squared right here, that cancels. This n squared and this n squared cancels. Here with the 3n, I've got a 3n over an n squared, so one of the n's will cancel. So this n will cancel with one of the n's right there. So that'll leave me with the limit as n approaches infinity of 7, because the n's cancel, so we just have 7, plus 2 over n squared over 2 plus 3 over n. Now, I'm going to write this way just this one time just to sort of explain what we're doing here. But typically, I would never actually write this way. So those properties of limits that we had told us that if limits are separated by plus or minus, like if we have functions separated by plus or minus signs, we can take the limits of them separately. And if things are divided, we can take the limits of them separately. So we could write this way. We could say the limit as n approaches infinity of 7 plus the limit as n approaches infinity of 2 over n squared. And that'd be over the limit as n approaches infinity of 2 plus the limit as n approaches infinity of 3 over n. And whenever I do this, I never write that step. I always do that part in my head. But just to clarify what we're doing here, I'm writing it this one time. And you probably won't want to write that out either. So if I do the limit as n approaches infinity of 7, what is the limit as n approaches infinity of 7? It is 7. Because it doesn't have an n, so it's not affected by that at all. Okay? What is the limit as n approaches infinity of 2 over n squared? It's going to be 0. Because anytime you have a variable raised to any positive power in that denominator, then it becomes 0. You'd have 2 over 1, 2 over 4, 2 over 9, 2 over 16. That number just keeps getting smaller and smaller and smaller and smaller and smaller. So we've got 7 plus 0 on the top. On the bottom here, what's the limit as n approaches infinity of 2? It is just 2, because it doesn't have an n, so it's just that constant. And what is the limit as n approaches infinity of 3 over n? It's going to be 0, because you got a variable on the bottom, so it would be 3 over 1, 3 over 2, 3 over 3, 3 over 4, 3 over 5. That's just smaller and smaller and smaller and smaller and smaller fractions. Okay, so 7 plus 0 is 7. 2 plus 0 is 2. So the limit of this function as n approaches infinity is 7/2. Okay, if I go back to Desmos, oh, I think it's shut down. Oh, and now I don't know if I know how to get back to where I was. Where's it at? No. Sorry. I don't like when it switches to that tablet mode. Need to make it quit doing that. Okay. So if you were to look back at Desmos, that number that value was getting closer and closer and closer and closer and closer to was 3.5, which is 7/2. So no matter, like, as those n values get bigger and bigger and bigger, that fraction that you're going to have is going to get closer and closer and closer and closer and closer to 7/2. So it's never going to go above that. All right, so if we have a problem like example 2, for example 2, we want the limit as x approaches infinity of x minus 3x squared over 4x squared plus 3. So I told you on the last one we need to divide by the highest exponent in the denominator. So Liliana, what will I divide by for this problem? The x squared, right? So I'm going to divide all of my terms by x squared, and I'm going to be a little bit lazier on this. I'm going to do this like I normally would. I'm just going to divide everything by x squared, which means I've got the limit as x approaches infinity of, if I've got x over x squared, one of those x's will cancel. which will leave me with 1 over x, and then minus, here the x squareds will cancel, so it'll be minus 3, over, here the x squareds cancel, so I have 4, plus 3 over x squared. Questions there? So you're just dividing every single term by the x squared and then simplify. And so this time I'm not going to write all those limits separately. I'm just going to take the limits of all those things separately. So Jaden, if I do the limit as x approaches infinity of 1 over x, what will I get there? Okay, so as x gets bigger and bigger and bigger, right? X is 1, and then it's 2, and then it's 3, and then it's 4, and it's 5. What happens to 1 over x? What's the value of 1 over x? We'll have 1 over 1, 1 over 2, 1 over 3. It's going to get smaller and smaller and smaller and smaller and smaller, closer and closer and closer to 0, right? So 1 over x, anytime you have a variable in the denominator and the top is just a number, you're going to get 0, because at infinity, for really, really, really big numbers, it's so close to 0 that it might as well be 0, right? If I cut the pizza into a gazillion pieces, it might as well be 0, right? So 1 over x is our limit. 0 is our limit for 1 over x. Then, Nathan, when I take the limit as x approaches infinity of 3, what do I get? Okay, does it have an x with it? It does not. So since it doesn't have an x, like if I plug in x, I'm not really plugging it in because it's not there, right? So it'd just be 3, 3, 3, 3. It'd always be 3 because there's no x to plug in there. So whenever you have a constant, just a number, it's just that number. So we're going to have 0 minus 3 right there. Okay? So Lyra, on the bottom, limit as x approaches infinity of 4. What will that be? It's just 4. So if you have a constant number, it's just that number because the x it doesn't depend on. Emily, what about the limit as x approaches infinity of 3 over x squared? It's 0. Okay? And so you don't have to use this limit notation here because at this point you are taking that limit. You're figuring out what it would be at infinity. So 0 minus 3 is negative 3, and 4 plus 0 is 4. So negative 3 over 4. Okay. Questions so far? Okay, let's try another one. Okay. In this case, you might see something like this. I've got 1 is 2, 2 is 3/4, 3 is 4/9, 4 is 5 over 16, 5 is 6 over 25. So first of all, I've got to figure out what a sub n is. I've got to figure out a formula for a sub n, right? So, in this case, if I look, I know n is 1, right? So I've got 2, but then I got 3/4. I got 4/9. I got 5 over 16. I got 6 over 25. It might help if I make this 2 over 1. Let's just look at the denominator right now. What's the denominator look like it is? It is that n value squared, right? 1 squared would be 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. So that bottom number is just my n squared. Let's look at the top number. Okay, what do I have for the top number? Like here my n was 1, but I had a 2. Here my n is 2, but I got a 3 in the top. Here my n is 3, but I've got a 4 in the top. Here my n is 5, but I've got a 6. What? It is going to be n plus 1. Okay, so that one's a little tough to figure out the formula for, but the top is always your n plus 1 because the top number is, you got 2, 3, 4, 5 for 1, 2, 3, 4. It's always one more than your n. The bottom is the n squared. Okay, so what I'm having to find here is my limit as x approaches infinity of n plus 1 over n squared. So I'm going to show you a trick on this one. You could do exactly what we did on the last two problems. You could divide everything by n squared and it'll work and you'll get the right answer. But in this problem, since all you have in the bottom is an n squared, another thing that you can do for this is you can do a love connection. We've done love connections in here before, right? When we've got that single term on the bottom, we can divide both of the top terms. And so if I do that, it's going to give me the limit as x, or I guess I should be using an n here instead of an x. N approaches infinity of n over n squared plus 1 over n squared. So you can do this whenever you only have a single term in the bottom. And then we could simplify here. So if we simplify that, this is the limit as n approaches infinity of one of the n's will cancel here, which will leave you with 1 over n plus 1 over n squared. Okay, so Harper, what is the limit as n approaches infinity of 1 over n? It is 0. And Justice, what is the limit as n approaches infinity of 1 over n squared? Okay, so what we're at, when I ask that, what we're asking is when n gets bigger and bigger and bigger, what happens to 1 over n squared? What happens to that value? So you would have 1 over 1 squared, and then 1 over 2 squared, so 1/4, and then 1/9, 1/16, and 1/25, and 1/36. What's happening to that value of that fraction? Smaller and smaller and smaller and smaller and smaller, right? It's going to get closer and closer and closer and closer and closer to 0. So anytime you have any number, doesn't matter what in the world the number is, over a variable to any positive power, you're going to eventually approach 0, right? Because as that number in the bottom gets bigger and bigger and bigger, it gets closer, the fraction gets closer to 0. So in this case, we got 0 plus 0, which is 0, so our answer is 0. Okay. All right, here's our next one. Okay, I can, if I want, divide everything by x because that is my highest exponent from the denominator. Or in this case, because I only have a single term in the denominator, I can do a love connection. This one is a triple love connection here. If I do this, triple love connections are still legal. You could even do quadruple or as many love connections as you want, as long as there is only one term on the bottom. What you cannot do is an upside down love connection. That is not legal. Okay, so we can divide all these. So if we did that, we would have the limit as x approaches infinity of 3 over 2x plus 4x over 2x minus x squared over 2x. And so if we simplify that a little bit, we'll have limit as x approaches infinity of 3 over 2x. That will not simplify. Plus, right here, the x's cancel, and 4 divided by 2 is 2, so we just get a 2. And then here, we're going to have x over 2. Is everybody okay here? Again, if you want, you can do it the other way that we did the first two problems, but this is just a little quicker. For this, Jasmine, the limit as x approaches infinity of 3 over 2x. It is 0. Even though you have that 2 in the bottom and the 3 on top, it doesn't matter. You got the variable in the denominator. So this part is going to be 0. Okay? And then let's see, Skylar, limit as x approaches infinity of 2. It's just 2. All right, now, who's up for a challenge? Limit as x approaches infinity of x over 2. So, if you think of what you would do with numbers here, right? We're plugging in 1. That'd give us 1/2. Then we plug in 2. That'd give us 2 over 2. Then we'd have 3 over 2. And 4 over 2. And 5 over 2. And 6 over 2. And 7 over 2. And 8 over 2. And 9 over 2. And 1,000 over 2. And 1,000,000 over 2. And a gazillion over 2. All right? What's happening to that number? It's bigger and bigger and bigger and bigger. Because in that case, we're not taking our pizza and splitting it into more pieces. We got 2 people, and we just keep ordering more and more and more and more pizzas, right? So, you know, you order 5,000 pizzas, you got a whole lot of pizza for each person. The bottom is staying the same. So this is going to be infinity. All right, so when you have a variable in the top divided by a number, then that is going to approach infinity because it's going to get bigger and bigger and bigger and bigger. So this approaches infinity. So I know 0 plus 2 is obviously 2. What is 2 minus infinity? It is not infinity, but it is negative infinity, right? Because you've got 2 and you're subtracting infinity. So you're doing like, if you think of doing like 2 minus 0, 2 minus 1, 2 minus 2, 2 minus 100, 2 minus 1,000,000, 2 minus a gazillion, you're going to get negative infinity. So the 2 is nothing in comparison to the negative infinity there, and negative infinity is what you get for that. Okay, so this is the mathematical way to solve all of these problems, but there is a shortcut that I'm going to teach you. Because let's look back through at some of our problems. Like our very first one where I have 1 over n, that equals 0, right? This next one where I have 1 over x squared or 2,000 over x, those both equal 0. Whenever I had n plus 1 over n squared, that equals 0. So if I have bigger exponents on the bottom, it always goes to 0, right? So even if it looks something like n plus 1 over n squared, like I already knew that that was going to be 0 because n squared is going to get bigger a lot faster than the n plus 1. So if the exponents on the bottom are bigger, then it's going to be 0. And I've got something to help you remember this here in a second. Also, if we look at the ones that we did where the exponents were the same, right? If the exponents are the same, I had 7n squared and 2n squared, and what did I end up getting for that one? 7 over 2, right? And then the next one that we did there, I had negative 3x squared on the top, I had 4x squared on the bottom, I ended up with negative 3 over 4. So if the exponents are the same, you're going to look at those coefficients. And then the last possibility you might have is that last one that we just did. And here, my biggest exponent was on top, right? And when the biggest exponent is on top, it's either going to go to infinity or negative infinity. You will have to actually work it out to figure out whether it's positive or negative infinity. But if it's bigger on the top, it'll be one or the other. Now, so you should have this slide here that says Bobo Botno eats DC. Okay, this is how you're going to remember this. It's a very strange saying, I understand. But all of my calculus kids say Bobo Botno all the time. So Bobo Botno eats DC, and this stands for, and what we're talking about here, technically, this is used for horizontal asymptotes because that limit as x approaches infinity is your horizontal asymptote. We saw that when we graphed that one from Desmos. So this is for horizontal asymptotes, but it also applies to limits as x approaches infinity. So if it is bigger on bottom then you get 0. So that O right there, of course, is 0. Right? So your horizontal asymptote would be 0, which we're going to talk about on Thursday, or in this case, the limit is 0. If whatever you're dealing with is bigger on the bottom. If it's bigger on top, not 1. Now, let's explain what this means a little bit. If you go down the road, if you're going down 77 and you see speed limit, and underneath it, it says infinity, is that really a limit? It is not, because you can go as fast as you want, right? So that is not really a speed limit if it is infinity. So what this means is if it's bigger on the top, it's either going to be positive infinity or negative infinity, which technically is a limit that does not exist, because infinity is not a limit. Infinity is forever, so it's not a limit, right? You're not going to see a speed limit sign that says speed limit infinity. But if you did, it would be really cool, and I would want one to put up in my classroom somewhere to help us remember that. My husband works for DOT. Wonder if he can pull some strings for me. So if your fraction that you're dealing with is bigger have bigger exponents on the top, then your limit does not exist. It's either infinity or negative infinity. And then the last one, EATS DC, is exponents are the same, divide coefficients. So whenever I have something like the limit as x approaches infinity of 5 minus x squared over 6x squared plus x, I don't even have to do the whole problem. I see, oh, I've got x squared on top, that's my highest exponent, and x squared on bottom, that's my highest exponent there. So I would take that negative 1 from the top and divide it by the 6 from the bottom. Okay, the 5 and the x don't even matter, because as your numbers get bigger and bigger and bigger and bigger, their impact is smaller and smaller and smaller. The x squared is going to be much larger. So, Bobo Botno EATS DC, this can help you remember how to do these limits when you do your homework. You're welcome to use Bobo Botno EATS DC. So, you do not have to actually work all of these out. You can just look at the problem and be able to tell what happens for these. Okay? So, we've got to talk about a couple things with sequences and series, because this didn't look so much like sequences and series because we weren't listing out all the numbers. But a series is convergent if its sum gets closer and closer and closer to a given number as the number of terms increases. So in other words, if the limit of your sequence approaches a number, then it's called convergent. Okay? If a series is divergent, its sum approaches positive or negative infinity. So it's either going to get bigger and bigger and bigger and bigger, or smaller and smaller. When I say smaller and smaller and smaller and smaller, I mean more and more and more negative, like negative 10, negative 1,000, negative a million, negative a gazillion. Right? That's smaller, but also kind of bigger at the same time. So in order for a series, a sequence or series to converge, when we say converge, it has to approach either 0 or the limit has to approach a number. Okay? You can only find the sum of an infinite series if it's convergent. Let's think about what types of series are going to be convergent. So we've got two types of series that we talked about the other day. We talked about arithmetic. And arithmetic, we were adding a number each time, right? So if we started off with 10 and we added 4, we'd have 14, 18, 22. Okay, is that sequence going to get closer to a number, or is it just going to get bigger and bigger and bigger and bigger? If I'm adding 4 over and over and over and over and over again. gets bigger, right? If you add a number over and over and over again, it's just going to eventually get to infinity, right? What about if you subtract a number? Smaller and smaller and smaller, but not in the fraction sort of way, right? We're talking about negative 10, negative 20, negative 30, negative 40, negative 50. Eventually, that's going to get to negative infinity. So arithmetic sequences and series, whenever you're adding or subtracting a number, they never converge, right? Because even if you're just adding a teeny tiny number, like if you're adding 0.01, you have 0.01, 0.02, 0.03, 0.04, 0.05, it's eventually going to get to infinity if you go forever, right? Theoretically speaking. So arithmetic sequences never converge. Geometric sequences and series are sequences where we're multiplying by a number, okay? So if we can multiply by a number bigger than 1. So 1.2 or 7 or 100. All right, if we're, like, let's just do a really easy one. If we're multiplying by 2, if we start at 1 and we multiply by 2, we'd have 1, 2, 4, 8, 16, and so on, right? Are those numbers getting larger and larger and larger and larger, or smaller and smaller, or closer to a number? Just bigger and bigger without bound, right? They're going to eventually get to infinity, right? So if you have a geometric series where you're multiplying by a number bigger than 1, it goes to infinity. The type of series that are convergent that we're going to see are geometric, which means, for those of you who weren't here, multiplying, where we are multiplying with our r, or that number we're multiplying by, is actually, let me write this a different way, where r is between 0 and 1. 0 less than r less than 1. So we're multiplying by a fraction like 1/2. So for example, if I start at 1,000 and I take half of it, 1,000, 500, 250, 125, that number is going to get smaller and smaller and smaller, but it's eventually going to go to 0, right? It has a limit to it. So these are the only type of thing that we're going to see. So I love, this is one of the coolest problems, I think, that our whole textbook has. So let's picture this, because I think it's crazy. It's crazy that this is true. So we are going to have a race. And in this race, you know, like a 5K, they do these things all the time. You pay $25 to run. They give prizes at the end, right? So we are going to have a race, and we are going to advertise that in this race, every single person gets a prize. We don't know how many people are going to show up. There might be 20 people to show up. There might be 1 million people to show up. Okay? But we're going to run this race. And so the way that we're going to give prizes is this. We're going to have first place gets $1,000, second place gets $500, third place gets $250, fourth place gets $125, and so on. We're going to follow that pattern there for all the places in our race. Okay? And everybody gets a prize. Now, for this, we have to theoretically be able to split a penny. Because eventually, you know, when we get down to where Miss Hyatt's finishing in the super high numbers, then we're going to be down to where we've divided that 1,000 so many times that we might have like 0.0075 might be our amount, right? So for this to work, we theoretically have to be able to give people less than a penny. Right, so if we can transfer to your bank account 0.000721 of a penny if we need to for this. So for this to work, we can't like give everybody a penny if they actually get less than a penny. We have to give them exactly what they really get. So if we're going to do this, the question is, how much money should we have on hand for prizes? Right? How much money are we going to have to give for prizes? Now, to me, the answer is infinity. It seems like the answer is infinity, right? If you're going to give infinity prizes, you have to have infinity dollars. But it's not. This is so cool. So let do this in your calculator because we can't really do it. Okay. Or well, I'm gonna have you guys tell me what to add together. So we already got the first four prizes. The first four prizes are 1,000, 500, 250, 125. So that's the first four. If I add the first four together, that's $1,875. Okay. So somebody figure out how much is fifth place going to get. We do 125 divided by 2. What do we get? 62.5. So I'm going to add 62.5. So now I'm at 1,937.5. Okay. Tell me what sixth place gets. What's the next? 31.25. So I'm going to add 31.25. And so I'm at 1968.75. What's the next place get? 625. Okay. So now I'm at 1984.375. Okay. Give me the next place. 7.8125. Okay. It's starting to become not worth running all that way now. But 1992.1875. Okay. Tell me the next. 90625. So now I'm at 1996.09375. Give me one more. 953,125. And to do this perfectly, you can't round anything. You do. So I'm probably going to stop after this one. But now I'm at 1998.046875. All right. And then we would keep dividing that. So like the next person's getting less than $1. All right. And we keep doing this and keep doing this forever. So eventually, this is going to get closer to a number. It is not going to be infinity. What number do you think it might be? Looks like 2,000, and it is. So infinite sequences or series. First of all, they have to be geometric. You'll notice on your formula sheet underneath arithmetic, you do not have an S equals. Okay, so that S is for your infinite series. What we're going to do for this is a infinite series. We're going to say S equals, and the formula is A sub 1 over 1 minus R. Okay, so for this one, A sub 1 is 1,000. And what is our R value? What number are we multiplying by each time? 0.5, right? We were actually dividing by 2 probably, but that's the same as multiplying by 0.5. So this ends up being 1,000 over 1/2, which gives you $2,000. So you could have a race where you give prizes to every single person that's there, and $2,000 is all the money you have to have, which I think is crazy because it seems like that's wrong. But assuming you can give them the 0.007 of a penny that they actually got, then you need no more than $2,000. So if you like put a disclaimer, if you get less than a penny, we're not actually going to give you anything, then you would actually need just a little less than $2,000 there. So I think that is crazy, but kind of cool at the same time. So if you ever like see something that's got that sort of scheme to it, you'll know eventually you're not really giving anybody anything, even though you say you are. Okay, so here's another really good example, I think. And this came from our textbook as well. It's a little bit dated, but I think it, obviously could probably still apply. I am no economist here. I do not understand this really, really, really well, but I think I know enough to help you through this problem. So on January 28, 1999, Florida Governor Jeb Bush proposed a tax cut that would allow the average family to keep an additional $96. The marginal propensity to consume, MPC, is defined as the percentage of a dollar by which consumption increases when income rises by $1. Okay? Suppose the MPC for households and businesses in 1999 was 75%. what would be the total amount of money spent in the economy as a result of just one family's tax savings? Okay, so here's the idea. If somebody gives you $96, okay, and essentially tax cuts, that's what it does. You get more money in your check. So you get $96, right? You can either spend that money or you can save that money, right? So if somebody gives you $96 and you spend 75% of it, then that 75% is going to someone else, right? So let's instead of 96, let's use 100. Let's say somebody gives you $100. You spend 75% of it, so you spend $75. You keep the other 25 for yourself. So it doesn't actually go into the economy because you just kept it. But the other $75 does. And so let's say that you go to Justice's store and you buy something for $75 in Justice's store. Well, Justice just got $75, right? So Justice is going to take his $75. And then he's going to spend 75% of that. So 75 times 0.75. He's going to go spend $56.25. So he's going to go to Jaden's store. And he's going to spend $56.25. Well, Jaden just got $56.25. So Jaden's going to go spend 75% of that. So Jaden's going to go spend $42 somewhere. And then, if he buys something from Jasmine, Jasmine's going to take her $42 and spend 75% of that. And then Lakin is going to spend 75% of whatever Jasmine gives her, right? And so it goes on and on and on and on and infinitely, right? Eventually, just like with our race, it's going to get down to where it's such a tiny percentage it's doesn't really matter anymore. But what we want to know is how much money is spent in the economy just off of that $100 or $96 in this case. You're making a lot of generalizations here because every person did not get $96, but on average they got $96, and every person is not going to spend 75%. Right? You have to kind of make those generalizations. You have to decide on average what the people spend. Jaden may save every cent he gets. And Emily might spend everything as soon as she gets it, never save any money. But on average, like as a class as a whole, maybe overall we would be saving about 25 and spending about 75. So that's sort of how this works. So for this, what we're looking for is the infinite sum of that money, right? So we would take our sum would be the initial amount is $96. Okay, and then we'd have 1 minus the rate, which would be 0.75, right? So we would get 96 divided by 0.25. It's going to be like 96 times 4, so 96 divided by 0.25 is going to give you $384. So now whether or not it's actually working or not, I don't guess that's really been told yet. But that's why whenever President Trump said that he was going to give all these tax cuts, that it was going to make the economy so great that it wouldn't even matter that we weren't taking in as much money because we would make so much more money. Because the tax cuts are going to make everybody spend money and our economy's going to be great and we'll be winning all the time. We'll just get sick of winning. So that's the idea behind it. By spending $96, the government actually... it didn't really spend, I guess, by taking in $96 less dollars. By giving somebody $96, it actually spent $384 in the economy. So that's why a lot of times that politicians will say if they give these tax cuts, then it's going to make our economy so much better. Now, economy is difficult to predict because you had to make a lot of assumptions for that. We had to assume somebody was going to spend the money. We had to make averages of how much money they were going to get back. So it's not easy to predict, but that's sort of what economists do. You can see how it would get really complicated on figuring out what we think is going to happen when we do this. So, but this is a cool application of this too. All right, so notes have taken just about the whole time this time, but your assignment is here. It's all from the textbook. You've got like 8 minutes, so go ahead, either start on this or you can look at the stuff from yesterday, either one. So